right, we are live, it looks like. Let me double check. See if we have a signal. If anybody is on the live stream, feel free to comment and ask questions. Can you guys hear? Looks like, yep, we've got a thumbs up. We've got about 28 people viewing right now, which is great. So I guess, yeah, we got 35, 45 people. Hey, Jeff, thanks for joining. We'll just give it another minute or so before we get into all of the questions.
Okay.
Great. Nick, Noah, Chris, welcome to the stream. Thank you. Wonderful. Okay, well, I guess we can get started. So, hi, everybody. My name's Ruben Yao. I work for the marketing group within Microcenter. And as you might be able to tell, I was born in England. I'm not American originally. So I came to the US about 20 years ago and have been with Microcenter for about 8-9 months now. Joined last July. So recently, obviously with coronavirus taking hold in the US, we have done a lot of different things to try and help out our stores, our customers, and our local communities. And that's included everything from using our 3D printers in our stores to make face shields, to also donating PLA. So we donated, for instance, about 100 pounds worth of PLA filament to Nova Labs in Virginia that works with the VA. And we've continuing to do more and more of these types of efforts to help as much as we can. And so about a couple of weeks ago, internally, we thought, why don't we start folding at home? And so we set up a team. It's called Microcenter Official. And so if you join that team, you'll see all of the points that we have accrued so far. And as of just a few minutes ago, and I'm checking the stats here, so I'm looking to the side to check a different screen, but we're about almost 980 million points. And we've completed about 77,000 work units just in the past literally 2 weeks. We've had a tremendous response. We emailed our customers and they just jumped on board, and it's been an amazing response. You guys have been awesome, joining the team, contributing and asking away in our community forum. And we've had, like I said, just a tremendous response. So with that, what we thought we'd do is reach out to the Folding at Home team and see if we can get some more information about how this program works and what is the work that we're actually doing and how does it help. And obviously they've had a tremendous uptick in response overall. PC Master Race on Reddit had a really good promotion effort there, and they had an AMA with the Folding at Home team. NVIDIA, thank you to those vendors as well that also promoted on social media the Folding at Home project. So I got in contact with Dr. Bowman and invited him to have a live Q&A, and he graciously accepted. So welcome, Dr. Bowman.
Thanks. It's a pleasure to be here.
Great.
We're kind of here.
Yeah, right. As here as can be, I guess, in the virtual Facebook Live. So tell us a little bit about yourself. Where are you from?
That's a good question. I'm an Army brat, so I'm from all over the place, but mostly grew up on the East Coast and then did my scientific training on the West Coast, and now I'm in Missouri, so center of the country.
Right. So St. Louis.
That's right.
Right next to our Brentwood store, actually.
That's right. Exactly.
Yeah.
So.
Excellent.
found that to be a great source of components.
Good to hear. Good to hear. So, is your background primarily medical, or is it more software development, or how did you kind of fall into this kind of like dual discipline project?
Yeah, so I have quite the mishmash of things from my background as well. So I have a juvenile form of macular degeneration. So I lost a lot of my vision when I was 8. And this sparked a keen curiosity about biology, but the curiosity quickly met with the realization that experimental biology is not very accessible to those of us with vision impairments. But fortunately, I discovered in high school a love for computers, and I put those things together. So in my undergraduate degree at Cornell University, I basically did a make your own computational biophysics degree where my official major was computer science, but I also did minors in chemistry and biomedical engineering, and then went off to Stanford for a degree in biophysics, where I got involved with folding at home and the use of atomically detailed computer simulations to understand how some of the fundamental units of biology called proteins work. These are really the molecular machines that perform lots of the processes we associate with life, and they've always fascinated me.
Yeah, yeah. So, when you got involved in the folding at home project, so that was at Stanford, is that
That's
right?
right.
Okay.
Hmm.
And so that was Mr. Vijay Pandey was part of that at the time, right?
That's right. Yeah. So my graduate advisor, Dr. Vijay Pandey, started the Folding at Home project in 2000. So we're coming up on our 20th anniversary this fall,
Excellent.
and I got involved in about 2006.
Okay. And he still involved in the project?
He's still a great source of advice, but he's mostly shifted his attention to other things having to do with deep learning and venture capital.
Oh, okay.
Yeah, it's
Interesting.
quite the
Yeah.
transition.
Right, right. Excellent. So I was reading up a little bit about you, and I read that you were awarded the Thomas Kuhn Paradigm Shift Award in
That's right.
2010, right, from the American
That's right.
Chemical Society. So tell us a little bit more about that.
Yeah, so my focus during graduate school originally was on understanding how another biomolecule called RNA folds. And as I got more and more into this, I realized that, with folding at home, even then we had some pretty amazing compute power, and we could generate a lot of simulations, but I felt a little stuck with what to do with all of that simulation data. And so I got involved with some uh, ideas that were bubbling in the lab about what are called Markov state models, which is a way to take all of these independent simulations and incorporate them into a map, essentially, of the different structures that a protein takes on and how it moves about between these different shapes it can adopt. And so I got very passionate about developing methods for how to build these models and use them to gain insight into protein folding. So how do these amazing little molecular machines spontaneously assemble into functional structures? And I like to tell people it's kind of like if you laid all the parts of your car out on the street and they magically sprung together on their own into a functioning car without a mechanic or an engineer doing anything. It's just really fascinating that it happens at all, and we wanted to understand the process. And so I was able to make some nice progress with gaining insight into this very basic research question using the Markov model methods that I developed for analyzing and accelerating simulations.
Wow. So when I work on my car in the driveway, there's always like some nuts and bolts left over, right? So,
That's
and
right.
I'm always missing that 10 millimeter socket for some reason. Um, so, did you kind of come across any of those kind of uh, software problems?
Oh yeah, I got to get involved with all kinds of development issues and yeah, learn some of the more professional software development tools. So it was a good time and got some general insights into principles that are common to the folding of many different proteins. And one of the exciting things about this is that having understood how folded proteins assemble themselves set us up to really start asking questions about how all the moving parts that these molecular machines have come to play in their function and malfunction, and new opportunities that this insight opens for developing drugs and other therapeutics.
Right. So is this software that you developed, is that still in use today?
It is, yeah. So I started a software project called MSM Builder, and people from Vijay's lab had continued to develop that, and that's still in use. And now there's at least 2 other software packages for taking all of this molecular simulation data that we and others in the community are generating and building these maps out of that data.
Okay, and this is open source software, right?
That's right. This is all open
Yeah.
source.
Excellent. So right now you're also with the Washington University in St. Louis,
That's correct.
right? And so can you tell us a little bit more about your involvement there?
Yeah, so I'm an associate professor at the Washington University School of Medicine. So I'm in our Department of Biochemistry and Molecular Biophysics. And so, my full-time job is running a research lab where we're really focused on understanding how distant moving parts of a protein communicate with one another and how we can exploit that for the design of new drugs and proteins, for example. And so my role in Folding at Home very much synergizes with that because it provides us this great platform to gather the data that we need to start addressing these questions. And so at this point, actually, my lab is roughly 50-50 split between computational people who are focused on continuing to develop the algorithms that we use for running and analyzing these simulations and then applying them to understand a variety of different proteins involved in diseases like Alzheimer's and Ebola and antibiotic-resistant bacterial infections and obviously now COVID-19. And the other, about half of the lab, is primarily experimental. And so it's an exciting time where the computational methods have come far enough along that we can really integrate them with experiments with one lab to quickly iterate between making computational insights and predictions and then designing and conducting experiments to test those insights.
That's interesting. So does that mean that with the kind of explosion of the interest in Folding at Home that you now need to dedicate some more resources to the computational sort of half of that lab?
That's right. That's right. So my experimental team has been doing really great. A bunch of them had been involved to varying degrees in computational research as well, and they've been stepping that up to help carry the load that we have the privilege of making use of now, and then they've also been helping out with our social media. So if you've been enjoying all the content that we've been creating on our blog and Twitter account, for example, a lot of the credit goes to a team of 3 students who have been spearheading that effort.
That's great. Yeah, I read a couple of weeks ago one of your blog posts, and it was talking about the coronavirus. In the media we see an image of this, and it is a sphere with these little kind of protrusions coming out around the outside of it or the periphery. And so it was really interesting. The blog post talked about each one of those looks like, and you called it like the demagorgan, right?
That's right.
It kind of, the mouth opens up, and that's part of the projects to do the modeling of how that moves. Is that right?
That's right. That's exactly right. So, there's some of the proteins that we work on where the people's default assumption is that there isn't maybe a really significant role for proteins moving parts in their function. And so in a number of these cases, we've discovered, what were largely unexpected moving parts and their role in these proteins' functions. But the spike is a really fascinating one because it's well appreciated that this protein has to have some significant moving parts in order to function. So it's actually comprised of 3 proteins kind of arranged in a ring, and the interface that actually binds to a human cell and initiates infection is actually buried when these proteins are closed up. And so this protein actually has to open up in order to expose that interface and have a chance of engaging another protein on the surface of a human cell. And so this opening motion, as we envisioned it, reminded us of the mouth of one of these demagorgan monsters from the television series Stranger Things.
Right, right. So
It's been hard to characterize the open state, and so the idea is that we can actually see this opening motion and see what the open state looks like in our simulations.
mhm. So there's a process that I also read about called X-ray crystallography.
That's right.
And yeah, how does that work? And then how does the Folding at Home project kind of complement that?
Yeah, so crystallography is one of a couple of really valuable experimental techniques for solving the structure of a protein. And the basic idea is that it's a lot like taking a photograph of a protein, but with a very short wavelength light, actually X-rays, so that it will bounce off of individual atoms. And just as your camera can take the ways that visible light bounces off macroscopic objects, people have developed ways to infer the structures from the way that X-rays bounce off of proteins. And one of the complications with this technique is that in order to get enough signal, you can't just look at an individual protein. You actually have to trick your protein into forming a crystal lattice. So a repeating unit of the protein stacked on itself in 3 dimensions, right? So what you're actually seeing is X-rays bouncing off of many copies of a protein. And so what you end up seeing is what the protein usually looks like, right? And so usually you're blind to the moving parts that the protein might have. And so what we're able to do is take this extremely valuable experimental data and use that as a starting point for our simulations, where we're able to watch how every atom in this protein moves throughout time. So we're basically taking that as the initial conditions and then building many movies of what the protein can do as time progresses. And using this, we can start asking questions of, what parts are moving, and is it more probable that this part moves or that part moves, and what new opportunities for designing therapeutics does seeing these alternative structures that weren't obvious from the experimental data open for us.
So how did you determine that it was one of the sites within the spike inside that actually bound to that ACE2 receptor site on the human cell? How did that
Yeah.
research come about?
No, so there's been a lot of experimental work on this. Some of the most direct evidence comes from actually solving structures of part of the spike protein bound to part of this ACE2 receptor using X-ray crystallography. So
Okay.
people have seen the details of what that interaction looks like, and they've also solved structures of larger portions of the spike where you see that the protein is usually closed up. So you can say, this interface that binds to ACE2 in this structure is actually buried in this more full-length structure of the spike.
Got it. Okay. So I'm going to ask like a really kind of poor man, like layman's question here, but why do we have to attack this, with using therapeutics, attack this particular receptor site that's buried inside of this spike? Why can't we find something that just attacks it from the outside?
We potentially could. So there's potentially lots of ways to tackle this, and the idea is to uncover as many of them as we can, right? So if, for example, we only had the structure of the closed state of the spike, we might have some ideas for what we could do with small molecules or antibodies, for example, to try to target that structure. But the more structures we see, the more opportunities we can open up, right? So we might see that one of the open structures actually has a binding site that we wouldn't have guessed was there based on the closed structure, and that might give us a new starting point for developing potential therapies that may turn out to be more fruitful from information based on fewer structures, for example.
Okay, so once we find one of these sites, the idea is that the therapeutics will be able to find their way into that particular site to
That's
break
right.
down that
Yes.
protein, or how does that work?
So what we're seeing is that the protein is actually undergoing these motions all the time, right? And maybe the most likely configuration of the protein is this closed state, but it could spend significant fractions of its time in different open or partially open states. And so those are also potentially useful targets. And we're doing similar things with many of the other protein components of the virus, where it's less obvious based on existing information that there might be as important moving parts as we know there are for the spike. But nonetheless, we're all already starting to uncover what we call cryptic pockets because they're absent in the available experimental structures, but we do see them open up in our computer simulations.
Interesting. So, I want to move on to what a lot of people have been asking about. Thanks for all of the questions that are coming in so far. But it's actually about the folding software itself.
Mm-hmm.
So obviously we've a lot of us have installed the client application on our PCs, and a lot of our customers have got some pretty high-end PCs. And in fact, funny little story. So our stores, so we've got 25 stores around the country, and they have installed the folding at home software on a lot of the demo machines. And we have some pretty powerful AMD-based Threadripper machines with dual NVIDIA 2080 Ti graphics cards, and they are powerhouses when it comes to cranking out the work units. But we have many of the demo machines running the application. So
that's awesome.
Yeah, I mean it's been really quite fun seeing the progress with the team. I want to call out our Mighty Mayfield store. That's the leader in our team. They've cranked out 1,800 or almost 1,900 work units, and they're the top of the chart when you look at.
All right, great.
So yeah, almost 178 million credits that they've amassed just by themselves in literally the past almost 2 weeks. So good job, Mayfield. But yeah, so the software obviously will make use of the CPU as well as the GPU. So
that's right.
How does that work? Like the projects, when they come about, how do you prepare them? And then how do you determine which ones are going to be used for the CPU versus the GPU?
Yeah, so under the hood, we have two different software packages that Folding at Home uses for actually running the simulations. So you can think about the software running on your computer as a wrapper that can run either of these software packages under the hood. And each has certain assumptions and strengths. So one is called GROMACS. That's the one that we use on CPUs. It can also make use of GPUs, but apart from Folding at Home. But for historical reasons, we are only able to use the CPU cores right now. And the other is called OpenMM, and it was designed to run entirely on a single GPU. GROMACS has been around for quite a while, and there's a lot of really valuable algorithms that have been incorporated into this software. And so some of those are in GROMACS, but not OpenMM. So specifically right now, we're in addition to looking at the dynamics of the individual proteins or complexes of proteins from the virus, we also have a lot of small molecule screening efforts underway where we're actually simulating the proteins in the presence of different small molecules that one can either buy on the internet or synthesize experimentally. And what we're doing is using the simulations to determine which of these compounds is most likely to bind more tightly to these proteins and serve as a valuable starting point for drug discovery efforts. Right, and so right now those can only be run on GROMACs on CPUs, for example, but there are related algorithms, other algorithms that are only in OpenMM right now and are only available to us on the GPUs. And so the decision tree is basically figuring out what the question we want to answer is and what simulations we need to get running in order to address that question, and then asking which of these two software packages is more compatible with addressing those questions.
Right. So that's the computer science half of the team that I guess is involved in preparing those projects.
That's right. Yep, we've been spending a lot of time spinning up more server infrastructure in order to
Yep.
queue up simulations and collect all the data from our volunteers, and setting up new simulations to ask all of these different scientific questions that we're going after. With the number of volunteers we have now, it's a really exciting time where we can do a lot in parallel. So we've got these small molecule screening efforts underway. I think we're currently screening over 50,000 compounds with plans to spin up more. And we're running simulations of every one of the viral proteins that we can get a reasonable starting structure from, either from structures directly from the SARS-CoV-2 virus, or from making educated guesses based on related viruses. And we're starting to think some about antibody design as well. So.
Interesting. And is that, say, the new projects like antibody design, is that something that is, are you working with outside groups that are asking you to help?
That's right. Yeah. So we have a number of experimental collaborators. And so there's some projects that are really driven by our own intrinsic interests. So my lab has been hunting for these cryptic pockets, for example, that again are absent in the available experimental structures, but that we often uncover with our simulations. And we've also teamed up with experimental groups who are doing small molecule drug discovery and antibody design, so that we can iterate back and forth between computational predictions and experimental tests.
So how do you decide which projects to take on? I can imagine, with all of the news about how much crazy computing power you have available to you.
That's right.
Are you just flooded with inquiries now from various groups?
There's quite a bit of interest, and most of it is internal decision making. So my group is one of the lead groups in the project, and there's two other groups that are heavily involved. So John Kadera at Sloan Kettering and Vince Voles at Temple University. And so we each have our different areas of expertise, and are largely asking questions within those arenas. So Vince and John have been doing a lot with the small molecule screening, and John has started thinking about the antibody design aspect. And we've really been thinking about things like cryptic pockets and the opening of this spike complex, and the experiments that we could conceive of doing to go along with those computational models.
So this is a question that we had submitted to us before in a community forum by Tramp78. So thank you for your question. And they asked, before coronavirus, what other diseases were being worked on?
Oh, that's a great question. So yeah, we did have these three different labs who were heavily involved in folding a home, and we've got a couple of others that have joined recently. And so John's lab, for example, has really been focused on questions related to cancer. Vince has been doing a lot of things related to peptide design, for example, and my lab was doing a lot with looking for cryptic pockets and a range of applications from Ebola virus to Alzheimer's disease and antibiotic resistance. So we've got quite a lot of breadth in terms of the applications that we can go after. And so this is one of the exciting things about the project, is that it's really a platform for biomedical discovery, both in terms of understanding the basic biology that allows us to function properly, and also, thinking about how things malfunction or how infectious diseases work, and how we can correct that with therapeutics. And so this is one of the interesting points that I really want to highlight with people as often as possible, is that we really only were able to pounce on the COVID-19 pandemic because we already had 30,000 active volunteers who were helping us to tackle all of these other diseases, for example. And so I hope that even after we hopefully get COVID-19 under control, that people will appreciate the utility of this approach and continue participating in the project and help us go back to working on these other diseases.
Right. So when you install the client software, there is a setting within the configuration that allows you to choose which types of projects that you want to participate in. And so
That's right.
I think the default value is any, but then
That's
you
right. Oh.
Alzheimer's. So
Yeah, and I think we lost your
yeah,
audio.
no, here I am. Apologies, small
No problem.
technical hitch there, but okay. So within the client, you can select different options, from any to four other different options. But when you choose any, we have heard on the actual Folding at Home forum, because you guys have a great forum as well, where you
Thanks.
provide a lot of support to prioritize the COVID-19 projects and work units, that we should just leave it on any. But
That's correct.
within that setting, what other projects kind of get funneled through?
Yeah, so we still have some projects that are up on some of our work related to cardiovascular disease and cancer and Ebola, for example. But that's very much a minority of what's going on right now. And all of our effort of late setting up new projects has been intensely focused on COVID-19. So we've left some of these other projects up and running in the background just because, as people know, the growth in our user base has sometimes outstripped the speed with which we can get more server-side infrastructure and projects up. And so rather than leaving people sitting idle, we'd rather get some useful science done. But the vast majority of what we're doing now is COVID-19. And we've actually been working on an update to the client that will allow everyone to select COVID-19 explicitly as a priority. So that will be coming soon, and you can stay tuned on our blog and Twitter and Facebook and LinkedIn to hear when we're ready to release that.
So when the new release comes along, will we have to download an update to the software?
That's right.
Okay.
Yep.
Great.
So we'll be trying to notify everyone via our social media that it's out, and hope people will help us spread the word.
Yeah, we definitely will. We'll make sure that we get all of the new software installed across all of our demo machines as well.
Perfect.
Wonderful. So let's just talk about the growth of the Folding at Home project. You mentioned 30,000 clients or machines that were running, probably a month ago or so.
That's right. Yeah.
What is it now?
So a month ago we were somewhere in the realm of 30,000. Now we're well over 2 million devices that are running Folding at Home. So it's been really tremendous, and it was funny because we've put a lot of effort into making our software infrastructure scalable, and had been eyeing building up to the level of having a million participants, and so we were well set up to handle the first 3 to 5-fold expansion of our volunteer community. But then, within the first 2 weeks, we had 400,000 new people download and start running folding at home. And so even then, we were pretty quickly stress testing our server-side infrastructure, and with likelihood that it would continue to grow. And so we've been reaching out to lots of new partners to help us get more server infrastructure running. And so we're very grateful to people like Microsoft and Oracle and Cisco and Avast and Linus Tech Tips, and I'm sure I'm forgetting someone, and I apologize that I can't keep it all at the forefront of my mind. But it's been really useful to engage with these various partners who have helped us spin up instances on the cloud and try to keep up with the growth of the project.
Yeah, there's another fun little story here about Linus. So with that Threadripper CPU launch that we worked with AMD a couple months ago now, as part of that promotion, Linus came out to our Denver store and he built one of these machines. It's like a $10,000 machine. And, this wonderful Threadripper processor and dual NVIDIA 2080 Ti graphics cards. And
awesome.
So we've got the machine still in our store with a little picture next to it to show like, oh, here was Linus, at the store building this machine. And so we installed the clients on that, and that's actually part of our team now. So sorry, Linus, but that machine is actually on part of Micro Center official now.
All right. Well, I think this is one of the great things is we can have some friendly competition, but I'm sure they're also happy to hear that one more powerful machine is contributing to the cause.
Yep. So I remember 2 or 3 weeks ago, you tweeted that the Folding at Home project had just passed the 1 exaflop barrier.
That's right.
That's incredible. What does that mean, and where are we now?
Yeah, so just for context, the most powerful supercomputer in the country is somewhere around 150 to 200 petaflops, and so with our best estimate being now that we're at something like 2.5 exaflops. So well above an exaflop. And so this is a really exciting time. I mean, there's been a lot of effort going into designing new supercomputers that will cross the exascale barrier, and it's fun that this community-led effort has gotten there. And it's also worth mentioning that this is a nice pattern with folding at home. We also hold the Guinness Book of World Records for being the first to achieve the petaflop level, and so it's fun to get to exascale first as well.
Excellent, congratulations! That's an awesome milestone. So, how many more exaflops are out there?
Oh my goodness, there's quite a lot. I was doing a little bit of research on this recently, but we have something around 700,000 GPUs that are running folding at home right now. But to the best of my knowledge, tens of millions of these things are being sold every year. So even with the tremendous size of folding at home, there's a lot of untapped from the perspective of distributed computing compute power out there.
Yep. Yeah, I mean, the number of PCs and consoles as well that are sold, because the client was also on the PS3 at one point, right?
That's right. Yes, this was a really fun thing while I was at Stanford, is that teamed up with Sony to get folding at home running on the PlayStation 3, and we're really able to showcase the power of the cell processor that they had developed. So it was cool. I think there were 8 cores in those machines, and 7 of them were actually running the simulation, and 1 was dedicated to rendering it in real time at the pace that the simulation was running, so that you could watch the simulation progress in real time.
So that's the output of the simulation work and all of the calculations.
That's right. That's right. So you could watch all the atoms in the protein wiggling around and undergoing different structural changes.
Yep, excellent. So the other projects that you said, the cancer, Huntington's, Parkinson's, and
Mhm.
Alzheimer's, are they kind
Mhm.
of on hold for right now? Since you said before that pretty much COVID-19 is like your top priority.
Pretty much. Like I said, we've kept some of the projects that we had running before this all took off going, and but basically all of the new simulations that we've been spinning up have been COVID-19, and most of our intellectual energy has been going into that as well.
Yep. So the actual work units that get distributed to the various
Hmm.
clients,
Hmm.
how does that work? Like, how do you determine how many work units make up a project, or
Hmm.
how does that work?
Yeah. So oftentimes when we're starting up these projects, we only have maybe one experimentally derived structure of what the protein usually looks like, and so one of the interesting things is that everything at this length scale is very stochastic. So if you take the exact same starting structure and start multiple simulations, they're not going to do exactly the same thing necessarily. And so oftentimes what we'll do is start up 1,000 independent simulations so that we can get a sense of uh, what the uh, breadth of possibilities the protein can perform are, and also what the relative probabilities of these different motions. Um, in other cases, we do have multiple structures, and we'll make use of that, but that is a typical use case scenario. And then the sizing of the work unit. So the idea is that the first volunteer who gets assigned one of these simulations will take that starting structure and run the simulation for a fixed amount of simulated time, and then they send back the data, and we take the last frame of that movie essentially and add it to the queue to be handed to the next volunteer. Um, and so the choice of the length of the work units is really based on how big the simulation is and how long it will take to perform on a typical machine, because we want to make sure that it's on the orders of hours or maybe a day on most machines, so that people can complete the work unit in a reasonable amount of time and send us back the data. Because what we want to avoid is people having work units that take a month to perform, for example, and 2 weeks in, their hard drive dies, or
Right.
they go on vacation and don't and shut their computer off for a week, and then we're sitting there waiting for that valuable data that they've generated but not yet copied over to our servers.
Yep. Yep. Yeah. It's pretty interesting that you're talking about the time taken to process work units, because when, I don't know, maybe about 15 years ago or so,
Mhm.
I first heard about the Folding at Home project, and I started folding back then. And gosh, the time it took to complete a work unit, and
That's
the
right.
score that you got was, it took so long.
That's
Just to
right.
get the first 100 work units was months and months and months of my machine just cranking away. And
That's right.
computing has progressed so much that I just built a PC about 4 weeks ago, and loaded up the software, and um, you know, I'm into the millions of points now just within a couple of
That's right.
weeks. It's been incredible, the difference that it's made.
That's right. No, Moore's Law and all the effort that has gone into optimizing these simulation software packages and the clever analysis techniques that we and others have developed, those have all been good to us in terms of really being able to improve the performance of these calculations. So part of it is all of those improvements, and part of it is a change in people's typical use cases of computers. Back 20 years ago, when most people were using desktops as their primary form of computing, it was more reasonable to assume that those machines would be on for days or weeks at a time, and that you could run one longer work unit and have a reasonable chance of getting the data back. But as more people have shifted to more mobile devices like laptops, where it's more common to turn them on and turn them off, for example, or not to want to run it while you're on battery power.
Mhm.
We've changed our strategy also in response to that to make sure that we minimize time spent waiting for a machine to come online and send us back the data that it's already generated.
Yep. Yeah, I noticed when the laptops are on battery power only, then the work kind of pauses.
That's right.
Yep,
Yeah, we don't want to cause anyone headaches by burning through their battery time when they weren't expecting it.
sure. Yeah, I was quite surprised when I loaded the software up again just a few weeks ago, and once I got it cranking, the resource monitor showed 100% utilization on the CPU, and again, same thing with the GPU, and all of the fans kicked up to 100%. It
That's
heated
right.
the room pretty good.
Ah, yes, I'll bet. I'll bet.
Yeah. So, how do you determine if the project is really relevant for a CPU or a GPU? And then also with, I know you talked a little bit about that before, but some of our questions that are being asked here are really about the specific configuration. So sometimes you'll see in the log, it'll say, no units available for this specific configuration. So
Ah, yeah.
yeah, when you're assigning these projects, it looks like you're looking for very specific hardware to run it on.
Yeah, so when we start up an individual project, we are able to specify what sort of hardware is compatible with that. So the simplest example is, there's certain algorithms that we can only run on CPUs and certain ones that we can only run on GPUs, right? So that's a decision that we have to make at the very beginning of spinning up a new project. And so from the perspective of one of our volunteers, what the software running on your personal computer is doing is assessing what your hardware configuration is and communicating that to our servers. And the first thing that the servers do is identify the subset of projects that your hardware is compatible with, and then basically flips a coin to decide which of those projects to assign you to.
Excellent. So, so that's why I guess then, with the massive increase in power, and you guys working through the night, I'm sure to get these projects
That's right.
prepared, that sometimes we just have to wait for these work units to be available, right?
That's right. Yeah, I mean, we really want to make sure that we put the compute power that people are entrusting with us to us to good use. So, we would rather ask for your patience if we're not haven't set up new projects than to spin up poorly thought out simulations that will keep your computers busy, but ultimately not have scientific value. And so, we've been reading papers as they've been coming out as quickly as possible and formulating more and more questions. Uh, and there's no end to the science that we can do basically. So our ultimate need for compute power is basically insatiable.
Mhm.
But we only still have 24 hours in a day, so the speed with which we can set up new projects is still limited. And so we appreciate people being patient for us because we do still need all of your help.
Yep. And so I know that on one of the subdomains you have stats.folding at home,
That's
you
right.
break down the number of processors and then also number of GPUs available that's broken out by AMD and NVIDIA. So
That's right.
we've got a question here from Kenny that is asking, are there more work units available for NVIDIA or AMD? Or how do you determine that?
Yeah. So right now, all of our GPU projects are equally compatible with both of the major graphics cards vendors. So there aren't specific projects for AMD or NVIDIA right now. The only real division is between GPU and CPU.
Right.
That's right.
Okay.
And there are some other knobs we can tune in terms of, some of the older graphics cards, for example, we won't pair with really big proteins, and vice versa. We won't pair some of the really powerful, new graphics cards with really small proteins because it just won't keep your chip at 100% busyness, and so we try to match people with appropriately sized systems to make maximal use of their hardware.
Got it. And so is that how the points are sort of calculated for each of the work units? Is kind of a multiple of the capacity of what your particular setup can produce?
Yeah, so the points come from our whole process for launching a new project. So what we'll do is run some initial pilot simulations on computers in our labs to make sure things are working properly in an environment that we can control and can handle if something crashes. But we really don't want to crash 100,000 people's computers. So when we're rolling out a new project, the first thing that we do is make it accessible to our beta team. And so, based on our internal testing on our own old machines, we get some sense of how long it takes to compute or to complete a work unit. And so we can make an initial estimate of how many points a project is worth based on that. And then we start sharing it with our beta team to make sure that we don't run into unexpected hurdles with the different hardware that people have set up, and also to help adjust the points that we've assigned to a given project. And then once we've gone through these quality control steps, we expand the availability of the projects to larger circles of our volunteer base. And so when you complete a work unit, your points are calculated based on what we call the base credit, which is our assessment of how long the work unit takes on a typical machine. But if you've registered with a passkey, and have returned a number of work units successful, then you're also eligible for our bonus program. And so basically what this does is gives you extra points in proportion to how much faster you completed the work unit than what we expected on a typical machine.
Yeah, that was one piece of advice that I had to try and propagate to all of the stores, which was get the passkey because it gets
That's
you
right.
lots more points, right?
That's right. That's right.
So the let me just go to a couple questions here from the stream. Okay, yeah, I've noticed this as well. So overclocking, Chris was mentioning in the stream about overclocking. So I noticed that when I tried to overclock my machine, that sometimes it would reject processing the work units. It came up with a message saying something like it's not compatible. Are you overclocked or something like that?
Yeah, so I mean, we really want to make sure that the results of these work units are accurate, right? And so we try to keep track of if people are doing things like overclocking to a great extent, because it can cause issues in the simulations where the data won't be scientifically relevant. And so we prefer people don't do these things actually.
Okay, so that's interesting because a lot of our customers are gamers and
That's
they
right.
do love to overclock their machines. So I
That's
guess that's one tip is if you want to be folding, revert the overclocking settings back to stock and then let your machine run overnight.
Yeah. I mean, we really want to minimize the chances of there being errors in the simulations that would make the results invalid. Because if you get some of these errors, it will result in the protein essentially looking like it exploded. And of course, that's not what's actually happening in reality. So while it looks cool when we visualize it on the screen, it's not actually useful for generating insight and designing experiments.
Okay, it's interesting that overclocking would cause that effect to the simulation data result.
Yeah,
So,
I mean, these are good things where people can really dig in on the forum, and I would invite our moderators on the forum to fact check me on what I've said here.
excellent. So let's keep going through the stream. We're almost at an hour. We've just got a few minutes left. So before we wrap up, so let me just scroll through and pick out a couple questions here. So Chris is asking, where physically or virtually are simulations being run, and who or what companies are leading this on?
Oh yeah, so all of the server-side infrastructure is run by my research group and these two other research groups that have been involved with folding at home for a while. So ultimately, the data is going back to Washington University in St. Louis and Memorial Sloan Kettering Cancer Center and Temple University, where the graduate students and postdocs and research staff in our labs are actually analyzing the data and seeing what we can learn. And given that Folding at Home is a publicly funded project, we've always tried to be very open about what we're doing. So, you can read about the projects through the descriptions that we have that go along with them. And we've generally shared the data upon request with other scientists. In the case of COVID-19, given the time-sensitive nature of the pandemic, we'd all like to see something come about in terms of therapies or vaccines sooner rather than later. We're making extra efforts to be proactive about sharing the data. So we're in discussions with a number of people about how to make these data sets available online to whoever wants to, because there's specific questions that we're prioritizing, but there's a lot of questions that one could ask with these data sets that we're generating, and we want to make sure in the same way that having more computers contribute to the simulations gets them done better, getting more scientists focusing their brains on the data and what we can extract from that hopefully will also accelerate progress.
Right. So how long do you think it's going to take? Do you have an estimate on when we can find that magic cure for COVID-19?
Oh my goodness, I wish I could give an estimate for that. And I think this is one of the tricky things, for science in general and this effort in particular, is that we're trying a lot of things that are very new technologically and scientifically to maximize our chances of finding something. But there's no way that any of us, whether experimental scientists or computational scientists, can give a detailed timeline for when we're going to hit particular milestones. So, really what we can say is that the more we can do, the faster, the greater probability that we come up with something in the near-term future. And along with that, we can point to some of the past successes with finding new ways to target proteins involved in antibiotic resistance, for example. And there we've actually designed and experimentally verified our first small molecules that target these novel binding sites we found and actually shut down the function of these proteins. And we've been doing similar work with the Ebola virus and have gotten as far as experimentally confirming the presence of a novel binding site that we discovered in our simulations and showing that it has the potential to, well, it actually does shut down the protein's function if you can jam something in there. And we were just getting underway with hunting for small molecules when we had to temporarily close down the lab in response to the stay-at-home orders. So getting back to that will be one of our first orders of business once we're allowed to return to the experimental space.
Yeah. So once you get through this this coronavirus, what's next on your list? A vacation,
Yeah.
perhaps?
That's right. Vacation, that sounds good. And, I'm looking forward to the days when Alzheimer's is the most pressing problem. I mean, I think, it's a serious problem, but
Yes.
not quite the same global impact with the immediate results of the current pandemic. So.
Yep. So is there anything else, as we're approaching the hour now, so we're going to wrap up. So thanks everybody for the questions and for participating and watching. Definitely appreciate it. Hope you enjoyed the discussion here with Dr. Bowman. So is there anything else you'd like to sort of mention to the Microcenter community?
Oh, we really appreciate your help, and it's great to see these grassroots efforts where people just get excited and get all of their friends and work colleagues involved. And we appreciate the enthusiasm, and it's helping fuel us to put some extra hours into doing this science as well.
That's great. Well, thank you, Dr. Bowman, and your team for all of the hard work that you're doing. And we're definitely very enthusiastic and very happy to be a part of this and be part of the team together to find a cure.
Thanks.
So with
Thanks so
that,
much for hosting
thanks.
this, and it was a
Absolutely.
pleasure to
Thanks
meet
for
you.
joining. Pleasure speaking with you. And so for the viewers, we will be taking this recording and posting it up on YouTube. So with that, we will bid you good night and farewell.
Good night.